Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Eleni Stark and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is Infrared Revealed, from data transfer to biometrics, basics of IR lighting. Our speaker today is our product manager, Celio Andrev. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during this webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have always the opportunity to ask us all your questions during the webinar at any time via the chat function. You'll find the chat function in our webinar control panel. The webinar itself will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email several days after the webinar. And you can also watch the recording of today's webinar a few days later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. And now I'd like to hand directly over to our speaker, Celio Andrev, and I wish you an exciting webinar.
Hello, ladies and gentlemen, and I also would like to welcome you to our webinar today. I will directly start first with a short overview of our topics and what we are going to cover for today. First, we will begin with a short overview about the infrared LEDs and what are their main parameters and what we need to look after. Then we will switch to our photodetectors, diodes and transistors, and then show you how we complete or make the perfect pair. At the end, I will conclude with some application examples and some advices what can be done and how we do it directly from our engineering desks. And then finish up with the question and answer. To begin first, I would like to start with a short overview of what makes the best infrared component and what are the main ingredients that we use in our kitchen to make the perfect component. Of course, the first and the most important part is the die or the chip or the infrared emitter or detector. In our product, we use pre-selected dies so that we have a really nice match of all the optoelectrical parts. Second most important maybe is the housing and the contact or how the electricity flows. Here we use in all our products gold-plated contacts for better contacting, better soldering, and better electricity flow, and industry standard packages for every product or for every application optimized. And the last part, this is the optical encapsulation and optimized for the emission and for the outgoing light. So we choose the right encapsulation. This I will explain later. But first, about the infrared LEDs and the dies or the chips that we have tested. At the end, we have two standard wavelengths that we offer from our product. This is the 850 and 940 nanometers. And what maybe you wonder sometimes, what is the difference between a peak and centroid wavelength? Basically, this is now an important parameter for the infrared products, where the emitter or the detector needs to see the emitter or the energy that is emitted. The peak wavelength, of course, as the name suggests, is the main emission wavelength or the wavelength with the maximum power, while the centroid wavelength splits the spectrum into equal energy parts. So the left part and the right part of the spectrum has the equal energy or the equal power. So basically this is more or less how a detector would view the emitter or the emissed energy. Uh, when we're talking about the emission energy in most of our LEDs here, we're talking about not the radiant power, which is the total energy, but the radiant intensity, which is also the milliwatt per steradian. This means how much energy I have in one uh, three-dimensional angle. Of course, this power depends on the viewing angle of the LED, and what we offer is powers from down to 1 milliwatt per steradian up to more than 300 milliwatt per steradian. Now maybe you ask yourself, how does this depend on the viewing angle? And this is basically given here on the next page. You can see on the picture the two different uh, emissions or the two different wavelength distributions. You can see a 30-degree distribution in the light blue curve and 140-degree distribution in the dark blue curve. You can see that a lot more power is concentrated in the middle in the short wavelength, in the middle in the short angle. Basically, this we can achieve with the correct encapsulation, with the correct form of our lens that is put on top of the LED. In our case, we offer available viewing angles from 20 to 150 degrees, and basically the difference here is the right application. Choose it for the right application. For example, if there is a short range wide angle detection, we will prefer to have a wide viewing angle where we cover a lot of angle or a lot of area with our product. Or if you have a long range application, for example, a camera that is used outside, then we need a really short viewing angle so that we can bring the energy as much forward as possible. Then talking about getting out energy or illumination or radiant power out of the LEDs, here we should discuss one more point about the infrared LEDs, and this is basically the turning on and off the LEDs. Before that, first important parameter is the switching of the LEDs. How fast I can turn on and off my LED. In the case, we're looking for very short rise and fall times, which means I have a higher switching frequency. For example, standard infrared LEDs have a rise and fall time of about 10 nanoseconds, which is equal to 100 megahertz. The 10 nanosecond is more or less the border in this case because of the parasitic capacitance and the junction capacitance that we have from the package. Uh, of course, the higher the driving current, the faster the switching time is, as you can see on the first graph. And then on the second graph, we would like to show you a pulse and the different measurement points. As you can see here, we measure between 10% and 90% of the optical signal strength, which for us is the standard measurement. Of course, you can find on the market measurements between 20 and 80%. This means that you can usually get up to 2 times slower uh, or faster switching time. Of course, this is also available with us, but we would prefer to show the main parameters in this case, or the whole picture. From the switching time depends also the pulsing capabilities, or how much I can pulse my LEDs. Uh, Pulsing the LEDs gives one benefit in this case. I can pulse my LED with a lot higher current than the permitted current in constant power, but in this case I also need to consider that with this higher current I have a few drawbacks. It means that my product will heat up, my chip will heat up, and then it will lead to lower lifetime and faster degradation. How can I cope with this? I need to let my product or my chip cool down. If we compute here a standard chip with 0.05 square millimeter pulsed at 700 milliampere, uh, with a small calculation, we go out and we come out with typical power density of around 1000 watt per square centimeter. This is more than you have in your kitchen uh, in a hot plate. So, because of the LED's efficiency of 50%, and 50% of this power will be emitted out, and 50% of this power will stay inside as a heat generation. The heat generation I need to then take away, and basically this I do when I read out my permissible pulse current graph, and I say, okay, for my pulse of 700 milliamps, I can do it with a duty ratio of 1%, and then I'm pretty sure that my LED will keep safe and it will not break down. So the maximum allowed parameters here will depend also on the packaging, on the chip size, on the duty cycle, or how fast I can cool down my LEDs. Now, I would like to conclude here the LED theme and come back later, and then uh, turn on to the photodiodes and the phototransistors. Because infrared LED is invisible for the uh, eye, you basically need something to detect this light. For detecting these lights, you need a photodetector. In most cases, this is a standard silicon diode, which is driven in reverse current. Uh, this is the quadrant 4. Uh, a diode is normally driven in quadrant 1. A typical solar cell application is quadrant 2, and then the detector is in reverse current. There are two main types of silicon semiconductor detectors, the photodiodes and phototransistors. Uh, the main difference is given in this table, why, in which case I need to choose a diode or transistor. Basically, everybody knows what a standard diode or a standard transistor is. The photodiode and phototransistor doesn't differ that much. A photodiode is a short switch on, switch off button. It has a photocurrent in microampere and switching time in nanoseconds. On the other case, a phototransistor is used more as a more sensitive part. It has a photocurrent of in the milliampere and switching time in microseconds. Due to the transistor gain, here we have a better sensitivity and lower switching time. So if we have a short on-off button, a photodiode. If we need something with more sensitivity, a phototransistor. Another application difference between the diode and the photodetectors is the daylight blocking filter. you can see the comparison between a product without a daylight blocking filter and a clear lens and a product with daylight blocking filter or a black lens. You can see that the daylight filter will block all wavelengths below 700 nanometers. It means that the light received there will come only from the infrared region. In most cases, applications for daylight blocking filter parts is where we have a lot of noise from coming from the outside light or from application used in the outside. And here I would like to know that even a daylight filter will not save you from direct sunlight because sunlight has a lot of infrared emission also. It's a black body emitter. So in this case, we always need to think about some protection or a shadow in this case. And now to put together the knowledge of emitter and detector together, we have created the perfect match. Our emitter and detector uh, that are available from Würth Elektronik. As you can see in the graph, we plotted the two wavelengths, emission wavelengths of the emitters and the daylight and no daylight filter sensitivity curves of the detectors. And you can see by both of them, we are more than 59% sensitivity, or what it means, more than 59% of the infrared light that is emitted for our emitter will be transferred into a current or into a signal from our detector. And this is what we understand of the perfect pairing between one emitter and one detector. Uh, if we go further, uh, we can see here uh, a wide range of products which are available from Würth Elektronik. We have, as I said earlier, the two standard emission wavelength of 850 and 940 nanometers with almost all available industry standard packages for the infrared emitters and a similar package for a photodiode and phototransistor. So you can choose the same size and form for your emitter and detector with or without a daylight filter. And we have a wide range of viewing angle from 30 to 150 degrees and optical output from 1 milliwatt per steradian up to over 300 milliwatt per steradian. If you are more interested in our product, you can always order our design kit with the order code 154150, where you will get free samples from each of our product, and what we offer that in this case is also free refill when you run out of infrared products. Now, after we talked about the general parameters, I would like to turn my attention to a few applications. Uh, Basically, what we see or what we don't see as infrared light is all over around us. If you just look around, you will see in each household a remote control for controlling our TV, or if we go to any public toilet, we will see a lot of automatic switches for water dispensation and for hygienic reasons. Uh, I guess in the recent years, everybody has his own biometric monitor integrated in his cell phone, or we are always happy when we go inside an office building and the door automatically opens before us. Oh, this is not magic. Oh, this is happening due to the infrared invisible light. But now I would like to focus our attention to some of our development in house. The first one is we decided that we also want to go with the trend and try to give something important for the colleagues in the company, how they can measure their blood pressure when they feel nervous or when their pulse goes high, because we not always have a very nice time together. And then we decided, okay, the best idea is that we decide to make our own pulse detector. For using the pulse detection, we use this non-invasive method of measuring the oximetric measurement of the oxygen saturation in the blood cells. Basically, what we do is we have one emitter and one detector. The emitter is emitting infrared light through our finger, and with the pulse uh, pumping heart, pumping blood through our vein. With every pump, uh, we get a fresh flow of oxygen saturated blood, and the oxygen saturated blood has a different reflection in the infrared region as non-saturated blood. So this difference we can basically detect with a detector. What we did is, uh, after we detect the light, is we just filter the signal of all noise, because it's a very weak signal, because the reflection part is not very strong. And then after we filter the signal, we can use some mathematics with the microprocessor, count the signals, and then calculate the pulse. Here you can see a short example of the signal data, and a short example what our colleagues, or let's put it this way, in this case we decided that this would be a nice student project to put everything inside with Würth Elektronik parts, and get a nice device that everybody can test internally. uh, Basically what we use here is two one low pass and one high pass filter, using capacitor and inductor from Würth Elektronik, and the only part that we didn't pr- provide is the uh, microprocessor. But with this, we can do real-time measurements, and you can see on the oscilloscope picture a very nice clean signal, uh, where you have each pulse uh, cleaned up and multiplied and amplified, so that we have a nice readout. All this is also available as application note, and people or you as a customer can read a bit more and and understand why and how this is done. It's really an easy job. Uh, the other application that we were talking about was all the data transfer, or how we can send information from one place to another. What we see here as benefit is that data transfer with infrared light, uh, or actually what I do when I press a button on my remote control and my uh, TV changes the program. This is a very nice example of data signal transfer. Compared to radio frequencies, it's easier to use, and the spectrum of infrared light is still free to use. So basically, you don't need to uh, register yourself or see if there is any possibility that uh, this radio frequency is already used from somebody. Another drawback or a benefit which we can see here is also that for each data transfer you need a direct signal or direct connection, optical connection. So it means that your signal will not go through any wall, but it also means that this will be a more secure connection, because Nobody that is outside the room or outside your field of view will be able to get the same signal. Uh, in most of the other applications that are used there, uh, due to the data security programs installed in recent time, this is a nice way to start your household measurements of your electricity, water, and heating, and transferring the data to external companies. This is why only people that have access to the device can read out the device and get the data out. Another application possibility is the different detectors. We already showed this in the oximeter measurements, where you have a transmissive or reflective measurement. The difference is transmissive measurement, you have an emitter and detector that is sitting against each other, and with interruption of the signal, okay, there is a presence, there is nothing there. Or a reflective sensor, where the emitter and detector are sitting at the same level, and if there is a presence or a body that will reflect the infrared light, then you can see, okay, there is something I still detected. Uh, the applications range from biometric measurements uh, to different household appliances. As for example, if you're wondering why your vacuum robot doesn't hit any walls or any chairs or any legs, one reason is that maybe they have a reflective sensor in them in there, so they can understand or recognize the ambient. It's also used a lot in different light barriers for security zones, or different automated doors for the elevator, or different hygiene and water saving dispensers in public washrooms. Uh, the applications here are more than immense, and we would be happy also to discuss even further applications. But with these final words, I would like to conclude my webinar, and just for a short uh, feedback and summary. Uh, since last year, Würth Elektronik welcomes you in the world of invisible light. On our website and in our catalog, you'll find the perfect emitter and defect and detector match and part, available with all the standard footprints, with wide range of viewing angles and power outputs for each application. And you find this as emitter or photodiode and photodetector, and a large field of different applications, which I leave to you to explore. But if you have any questions, you're always welcome to contact us or your local sales representative. Thanks a lot. And now I turn the word to my colleague Eleni.
So thank you very much for this great webinar, Celio. Now we would like to turn our attention to all your questions. Therefore, we will just wait a little while until some questions have come in. In the meantime, I would also like to draw your attention once again to the fact that you will receive the recording of today's webinar in a few days via a separate email. And there will also be the presentation in PDF format so that you can read everything or watch everything again. And it will be also available on our website or on our Würth Elektronik YouTube channel. So let's have a look into the questions. Somebody asked us if we can send him the link for the Optoelectronics design kit. No problem, we will send you the link. Also, we will just put it in the email for everyone so that everyone has that information. Yeah, this is not a problem for us. So the first question, is there a cost difference between detectors with daylight filters and without daylight filters?
Okay, Lenny, thanks for the question. Thanks, the the people taking the time in the webinar for the questions. First, is there a cost difference between detector with and without daylight filter? Uh, it's a nice question. In most cases, the difference in the price between a detector will come out from the detection or the chip built inside. So if we cover the lens black or not, this will not give a difference in the price.
Okay, thank you very much. So we will have a look if there are other questions. Oh, yeah. Which protective measures are necessary for infrared LEDs as the light is not visible for the eyes? Yeah, this is the question.
Okay, this is a nice question. In most cases, Würth Elektronik is following the IEC norm for photobiological test of LEDs. Of course, infrared light is not very dangerous for the eye because the photons have a lower energy. Uh, in any case, we measure all our LEDs for photobiological test and we provide the photobiological safety certificate uh, for testing the LEDs. In most cases, to add up here, the dangerous LEDs for the eyes are the blue emitters, where the energy of the single photons or the light bearing part has a higher energy, which means when absorbed, it will lead to more damage to the eye. So in this case, infrared LEDs are primarily safe for everybody, but if you need any support or any certificates, please contact us.
Thank you very much, Cilio. There's another question. Where can I find the components on Red Expert? So go ahead.
Uh, the components are on Red Expert. So if you go in the Red Expert, basically a web-based program where you can log in if you need to, but when you log in, you will get a lot more available data. It's a free login and no advertisement connected. And in there, if you go to the different products, there is a product group Optoelectronics. In the product group Optoelectronics, you will find the infrared components, and in there, you have a list of all the infrared components. This is for the LEDs. In the same uh, group or in the same list, you can find also a list of our photodiodes and photodetectors. And in Red Expert, you'll find all the different parameters that are available also in our datasheet. Download our datasheet or order your free samples of products.
And as this question has been asked, I will also add the link to Red Expert so that you will all have it directly in the email with the presentation and the link to the recording of this webinar so that you don't have to search for it. As I see, for now, we do not have any questions anymore, Chilio. So we will end up the webinar right here. If you have any questions after the webinar, you can just, as I said, email us at both email addresses. And we would like to thank you for listening, and we hope to see you for the next webinar again. Thank you very much.
Thank you and have a nice afternoon.